All right, Psyc124 students, welcome to part 2 of the video lecture for Halloween 2018. This is going to be hopefully quite a bit shorter than part 1, but just in order to keep us on pace, I have to talk a little bit about the analogy model, which is the first model, computational model of word naming that I'm going to be introducing in this unit, the first of 2 major models of word naming. So the analogy model is a connectionist model, and the particular version that I'm going to hold you accountable for on this exam, this upcoming exam, it is a connectionist model which is intended to make predictions and satisfy data about how people compute their verbal response when asked to read aloud a single word presented on a computer screen. In actuality, analogy models, if you've read the Kawamoto 1994 reading, are sort of a loose group of models that share some very similar assumptions about how pronunciations are determined. But most of these owe some debt to what's called the activation synthesis model that was proposed by Glushko in 1979. Glushko was a graduate student of McClelland and Rumelhart, who we have already seen develop the famous interactive activation model of letter perception. But the particular version of the analogy model that I'm teaching you is one of 2 computer simulation versions that were explored in Kawamoto 1994 in the paper, in the actually book chapter, One System 2 or 2 for naming regulars and exceptions. And in particular, the version that I'm interested in is what Kawamoto refers to as the dynamic model, the dynamic analogy model. And the reason that we are emphasizing the dynamic analogy model is that it is explicitly an extension of the interactive activation model. And so it really builds nicely on concepts that you had to understand for the previous exam. And what we're going to see is some of the assumptions of the interactive activation model will have been simplified just in order to help place the attentional emphasis, place the focus on the features that are important for reading aloud. That doesn't necessarily mean that some of the assumptions that have been dropped aren't actually there. It just means that that's not where the focus of the modeler is. Those aren't regarded as the key concepts. And a couple of assumptions have been extended, obviously, because as we reviewed, the interactive activation model, all it does is gives you an insight into what's going on with the sort of stored words in the head, which ones are being regarded at any given time over the time course of processing as more or less likely fits to the underlying stimulus. That model by default doesn't exhibit any sort of behavior, including any sort of verbal naming response. So what I have on the screen here is a restricted subset of the dynamic analogy model architecture. The architecture that I'm going to ask you to be familiar with is 3 levels, and here we are looking at the bottom 2 levels because these bottom 2 levels substantially overlap with things that you know from the interactive activation model. So I'm going to start here. What you're going to notice is that there's a couple of important abbreviations. We are no longer worried about a feature level. Instead, we're starting right at the letter level. And then above that, we have a word level. Again, not because features are unimportant. And in actuality, if the analogy model is approximating anything sort of close to the reality of human mind, that feature level is still there, but we're just not worried about modeling every little last detail for the purposes of this exercise. You'll notice that this is also, though it is based on the assumptions of the interactive activation model, as modeled, it is no longer interactive. And again, not to say that interactivity isn't important, but we're just dropping it as a crucial assumption for the effects of interest that we're targeting with this particular model. So we're no longer modeling the top-down connections from words to letters. So what we have here is we have a set of letter nodes, and as in the interactive activation model, these are positionally bound. Okay, so we're going to reduplicate 26 letter nodes at the letter 1 position, 26 letter nodes at the letter 2 position, the letter 3 position, the letter 4 position, and for simplicity's sake, we once again are assuming that this is a model for reading 4-letter words. And obviously, as you can see, the standard caveats for all these sorts of visual schematics apply, that not all nodes are shown and not all connections are shown. One thing I do want to point out to you is what you're seeing here in terms of the upward connections from letter nodes to word nodes. These are the excitatory connections. So on this schematic, what Kawamoto has done is used dashed lines to represent excitatory connections and solid lines to represent inhibitory connections. Now, the inhibitory connections from positional letter nodes to word nodes that are not consistent with those letter nodes, those connections are still there. Those connections are still there. They've just been omitted from the schematic in order to avoid clutter. Okay, so we are assuming that, for example, position 1 P node shares an excitatory connection with the pint word node, just as you would expect. But we are also, although they're not depicted, we are assuming that the position 1 P node shares inhibitory connections with the hint word node, the lint word node, the mint word node, and all of those word nodes that are not shown, which do not start with a P sound, or which are not, sorry, I should say which are not spelled starting with P, because these down here are letters. These down here are letters, so this is about the orthography on this level, not about the pronunciation. All right. So again, this model could accommodate the extra details, but for simplicity's sake and to save computer cycles and things like that, they haven't been included in this model. One important detail to bear in mind is that just as in the interactive activation model, word nodes here at the word level have different resting activation values, and those different resting activation values have been determined based on the printed frequency of the word. And in terms of our ability to account for the various naming time results, which I introduced to you in part 1 of this lecture, that's going to be critical to bear in mind. So we have letter nodes that all have sort of a similar ground state, resting activation state. We have word nodes, a layer above that, which have different resting activation levels. And those resting activation levels are determined based on printed frequency of the associated word. And just as an interactive activation model, all of these nodes can take on graded levels of activation between some minimum and some maximum, and activation accrues gradually over time as a consequence of stimulation and as a consequence of the spread of activation and inhibition throughout the network. And in terms of what letter nodes are excitatorily versus inhibitorily coupled with what word nodes, that once again is based on which words would be consistent or inconsistent with which letters in specific positions. So because we, for reasons that I'm not going to get into in this lecture, but which will be very important when we come back to this model and section next week, we're looking at a particular subset of words here: pint, hint, lint, and mint. As I already said, P shares an excitatory coupling with pint because pint begins with letter P. Hint shares an excitatory coupling with hint because hint begins with the letter H, and so on. But all of these word nodes will take excitatory signal from second position I, third position N, and fourth position T. Now you'll notice, and again, I'm not going to emphasize this so much for this lecture, but looking forward, it will be an important point that the I in pint here is pronounced with that long I sound, pint, whereas each of these are short I, hint, lint, and mint. But they all are taking excitatory influence from the same I in position 2, and that again is because this is about the spelled I. So the couplings here are based upon the spelling, going from this first layer to this second layer. Okay. So what do we need to add? What sort of third layer do we need to add to extend this basic system such that we can compute a pronunciation? Oh, by the way, I'm sure you noticed, sorry, I'm just looking at the schematic here and realizing I should have emphasized that we once again have lateral inhibition between all words on the word level. So all words on the word level are competing to be hopefully the sole clear leader in the race for the most activation. All right. Okay, so how do we need to extend this in order to have a system that computes pronunciation based on a spelling? And if you've done the reading or if you were paying attention on that very first slide, you already know the answer. But if that went by you because you weren't thinking about it yet, take a moment to think about, there's a lot of different answers that this question might have. What could we add up top in order to facilitate the computation of pronunciation? So Glushko's answer, and the way that Kawamoto in 1994 has implemented this particular simulation, is that we have a layer of positionally bound phoneme nodes. And again, we're going to have phonemes at each of 4 positions. You can come up with some caveats here because, of course, it's quite common for words that are spelled using 4 letters to actually only have 3 phonemes. We can come back and talk about that in section. There are some ways that you could get around that issue in terms of exactly how you formulate your phoneme level. But for now, we're not going to be concerned with that. So particularly if we keep the focus on the words that are being used in this schematic example, you'll note that each of these words in fact does have 4 phonemes. Remembering that, going back to the very first day of class, a phoneme is a fundamental contrastive unit of sound in a language. So for pint, we have the phonemes p, I, n, and t, right? Pint. For hint, that's bad. That H isn't going to read very well on this microphone. Let's say for lint, we have the phonemes l, I, n, and t. For lint, and so on. So what we're going to do here is we again have only bottom-up connections, no top-down connections. And we again, although we are only depicting excitatory connections, we are assuming inhibitory connections as well. So that pint wants to excite first position p, which is this. This is no longer p. So I disagree with Alan's schematic here. I think he should have used the slashes around the characters here to indicate that these are based on sound or pronunciation. So this is no longer P, whereas down here this is the letter P. This is now depicting the phoneme P. Hopefully that registers on the recording. This is now registering, this is representing the phoneme ol as opposed to this letter L, okay? So pint wants to excite first position P. And even though it's not depicted, it also wants to inhibit first position H, first position ol, first position okay? And so it is with the second position phonemes and the third position phonemes and the fourth position phonemes. This is illustrated very nicely by the fact that pint is the only one of these that wants to activate, to excite second position I, whereas the other three all want to excite second position I, okay? And so if you allow the network to run for a while and you are showing it a spelling of a word it knows, so for example, let's say we're showing it lint, we have activated first position L, second position I, third position N, fourth position T. Those all very clearly want to excite the lint node. You'll get some inhibition of these other nodes based on the inconsistent first letter. Lint will be competing effectively with pint, hint, and mint, and so before long we'll be taking the lion's share of activation at the word level, and lint in turn will be activating the first position ol, second position I, third position n, fourth position t, not t, fourth position t. And so over time, you will have clear winning phoneme nodes at each of the four positions corresponding to lint. And if I can return momentarily to our discussion of local versus distributed representation, which I introduced back when I gave the general talk on neural networks, what you will notice about pronunciation in this version of the analogy model is that the pronunciation, if we think of the pronunciation as a single thing, as a single concept, it has a distributed representation in the phoneme layer. So each of these nodes is a local representation node with respect to phoneme, but collectively they represent a distributed representation of pronunciation, okay? Because the pronunciation is a linear concatenation of the most active phonemes at each of the four positions. So in this case, we have a clear output, okay? For interactive activation model, you could sort of view the word level as the output, but really there wasn't an output in that, and the model wasn't simulating any sort of behavior. This model, what we've talked about so far, isn't quite simulating a behavior yet. Really, we're simulating the assembly of a pronunciation. That doesn't mean that the model is speaking yet. We're just simulating the assembly of a pronunciation. But that's sort of a clear thing that's going to be sent forward to, the motor system for behavior. And so in a sense, we have an output here, which is the pronunciation, which is the set of activated phonemes. Now, we're using this model to try and account for and make predictions about human empirical data from the naming task. Okay, so again, we should never lose sight of the fact that we're not just playing digital games here. We're not just making computer simulations to make computer simulations. The point isn't to make an AI. The point of this particular model is to try and come up with a numerically explicit account of human performance data. So all of this is sort of for naught if we don't have a way of simulating naming time, right? So we have to add on a couple more assumptions that are not shown. And this is similar to, the questions that I was asking in the last unit about how do you extend the interactive activation model in order to simulate lexical decisions, to get a sense of lexical decision times. What's happening up here is that, as I say, we are assembling or we are computing the pronunciation. How do we know at what point a pronunciation has been launched so that we can say, okay, that was when naming time happened. That was the end of the naming latency period. And there are different answers, once again, that you can supply to this question. And in fact, in about a week, I'm going to come to you with some arguments as to why the standard response, the standard assumption used in this model might be a problem based on work that's been done in our Reading Aloud lab at UCSC. But for now, I'm going to introduce you to the standard assumption, which is each of these phoneme nodes at the phoneme level has a built-in threshold. Each of these phoneme nodes has a built-in threshold, which is some value, whatever makes sense. 75% of total activation. Actually, modelers futz with where it is, but it will assume that each of these phoneme nodes has some threshold. And when a phoneme node has crossed threshold, we consider that phoneme to be selected for production. Further, we're going to assume that the pronunciation response is initiated once one phoneme has been selected for production at each of the 4 positions. So once you have one phoneme activated beyond threshold at each of the 4 positions, we consider the naming latency period to be ended and the naming response to be begun. And however many ticks or cycles of the simulation that took, that's equivalent to some amount of time, which is naming time. Okay. So for now, we will assume that the naming response is generated once one phoneme at each position crosses threshold, as I said. Now, if you read the Kawamoto 1994 paper, you will see that a theme that we're going to be addressing in Unit 2 is one of the key debates in naming research, and in particular in the theoretical side of naming research, in the cognitive theory side of naming research. This is the notion is one system or two. One system or two for naming regulars and exceptions. What do we mean by one system or two? Well, here's the thing. Most people in the modern literate world learn to read by phonics. And you know that, there's all sorts of exceptions, but, right, H is supposed to sound like h, and I, except in some cases, is supposed to sound like I, and N is supposed to sound like N, and T is supposed to sound like T. And although you have to be able to account for the exceptional cases, many people have the intuition that we sort of have a rule system built in, right? That we could go, well, if we see I here, it can be connected to the I sound. And then we have to have some logic in there that goes, well, except when you see it in combination with certain other letters, then it does something else. And then we have to be able to account for the exceptions, and generally it's assumed that we account for the exceptions by having memorized words, okay? We see a sequence that we know, and we know, oh, well, that word is pronounced like this. We see P-I-N-T, and we know that it's not pronounced pint. We have memorized that that particular sequence is pronounced pint. But then people get into this intuition that, well, for really high frequency strings, I mean, really, isn't it mostly recognition? Like, how often are we really recomputing the spelling to sound rules, even for words like hint, lint, and mint that are regulars, that are perfectly consistent with the spelling to sound rules? If they're words that we're used to seeing all the time, aren't we really just retrieving that pronunciation from memory? And this is the crux of the debate. How much do we have to account for rule systems, phonics rule systems, and how much do we have to account for retrieved pronunciations based on words we know? Now, what you'll notice in the analogy model is we don't have any sort of direct connections from letters to phonemes. What do we have? All of the pronunciation responses are mediated through the word layer. And this is a very important element of what makes the analogy model the analogy model. All pronunciation responses are mediated by activation passing through this word layer. That's going to filter how things occur. And so you can argue that this system does not include any spelling to sound rules. But is that really true? I'm going to go over this in more detail with you in section next week. So really for now, I'm going to ask you a set of questions. I hope that you will seriously ponder them because the answers are very, very interesting. This model, it does some I just find this model very, very interesting because it assumes that all the action is mediated through words you know. And so the natural thing to ask is, can this model name pseudo words? It doesn't. You have the exact issue that you have with the standard interactive activation model, where if you show it the spelling corresponding to something it doesn't know, such as a pseudo word, which it won't have memorized, it won't have in this lexicon implemented at this level, obviously there is no one best fit node that can come to activation more than the competitors, because no best fit node exists, right? So does that mean, in fact, that this model cannot name pseudo words? Think seriously about what is going to happen. And here are a couple of hints before I leave off for this lecture. When people discuss analogy models, they use some key terminology. And again, I'm going to be returning to these in section, probably at the beginning of Monday's time with you next week. There is a key concept in the notion of neighbors. Neighbors are words that differ by a single letter, okay? And so word nodes, in fact, all of the word nodes being depicted in this schematic are neighbors of each other. And think about the possible significance of that. And moreover, think about the possible significance of what are called conspiracy effects or gang effects. Remember that nodes can be partially active, okay? Remember that nodes can be partially active. Conspiracy or gang effects emerge in analogy models when you have multiple partly active word nodes that are sending activation to at least one common phoneme node. Multiple partly active word nodes that are all converging their activation onto at least one common phoneme node. And that's going to be important in thinking about what happens when you present a novel string, such as a pseudo word, to this model. Okay? So thank you for your attention. I hope that you find this interesting, and we'll have some more concrete answers for you in section next week.